So we've talked a lot in this module about different ways to atomize, and all of these ways use heat. And as we talked about using a flame versus using an ICP, we know that the ICP is going to be more efficient. It comes at a higher temperature. But what is it about this higher temperature that makes the ICP such a better choice when we're doing especially atomic emission or something that we want a really high percentage of our analyte to be in the excited state? So this video we're going to explore what we call the Boltzmann distribution, and this distribution is going to basically tell us about the population between the ground state and the excited state. So let's dive into that. Okay. Now, as we're talking about ground state and excited state, you might recall the Jablonski diagram, where we had a ground state and we had excited states. Now, when I draw this, keep in mind that for different atoms, there's different ground states and excited states. These are called degenerate states, and so we might have ground states that I'm going to say, they're at the lowest energy, E0, and I'm going to say that for this instance there might be two ground state options here. Okay. If an atom is in the ground state, it can, just like a molecule can, absorb energy, whether that's heat or light energy, and be excited to an excited state. Okay, these are at some kind of higher energy. We'll call that E star, right? So an increase in energy. And in this case, we're going to say that there are three degenerate excited states, and we'll call these G star. Now, how many degenerate states you have at the ground state and at the excited state is something that I will give you. I'm not going to make you kind of research that on your own. I'll give that to you in a problem. But we'll need those values in a minute, which is why I'm including them here. Okay, so for absorption, we're going from the ground state to the excited state. And for emission, we'd be dropping down from the excited state to the ground state. Now, the Boltzmann distribution here is basically just going to describe the equilibrium between atoms that are in the ground state and atoms that are in the excited states. Okay, and ideally, if we're going to have a increased signal, we're going to need more atoms in the excited state. If we can drive the equilibrium that's occurring between atoms in the excited state and atoms in the ground state to where the equilibrium is more heavily represented by excited state atoms, then we would have increased signal. Because remember, if we're looking for an emission signal, we need to get more into the excited state in order for them to be there to drop down and emit a photon off. Okay. So the Boltzmann distribution is a numeric way to represent the relative populations between the ground state and the excited state at a given temperature. So the equation for this says that the relative population, or the number of atoms in the ground or in the excited state, indicated by the star, relative to the number in the ground state, so how many atoms are in the ground, how many atoms are in the excited state, that ratio, is proportional to the number of degenerate states, the ratio between the degenerate states, and then some value that's dependent on this difference in energy, so e to the negative delta E, which that delta E is going to be your E star minus E0. So how much energy is the difference between ground and excited? And this E0 is divided by KT. Here K is the Boltzmann's constant, which is equal to 1.381 times 10 to the minus 23rd joules per Kelvin. So it's energy per temperature in the units, okay, joules per Kelvin. And the T here represents your temperature. So what temperature are we working at? Okay. So what you'll find in this calculation, and you're going to use this equation some in the group work to look at different temperatures of the flame versus the ICP and see how this particular ratio of atoms that are excited to atoms that are in the ground state changes as a function of changing this temperature. Now, as you do those calculations, remember to follow the units. These energy, this delta E, or difference in energy, is going to need to be in joules in order to make the joules cancel with the Boltzmann constant. And your temperature is going to come out in, or need to be in Kelvin in order to cancel those units as well. All right, so just keep those in mind as you're doing the calculations and explore this in the group work. See how changing the temperature changes your distribution here. And whether it's a big change or a small change, it will affect your distribution and the overall ratio of being in the excited state to being in the ground state.